Hello and welcome to my video on mirrors. So we're talking about mirrors and basically the different focal points and focal lengths and center of curvature and all that sort of stuff about converging and diverging mirrors, or convex and concave mirrors. So first of all, focal point of a mirror is the same as with a lens. It is the point where all the light rays meet. The focal length is the distance from the mirror to its focal point. This is sort of true, although this is actually more helpful. For a mirror, that you can imagine the mirror continues making a circle all the way around. So if we just draw this circle all the way around, you can maybe see that the center of this circle would be somewhere around here. And the focal length is always half the distance from the center of curvature to the mirror. Half of that distance is the focal length. So this is equal to 1/2 the center of curvature. Okay, and that's true whether you're on one side or the other. So again, center of curvature would be somewhere around here. And if you were to draw the circle, this is certainly a terrible circle, but you can maybe get the idea that if you continued the mirror around, you would get that center of curvature. And halfway between the center of curvature and that is the focal point. Now, what you can see is that is where if you shoot a ray directly into the mirror, it will bounce towards the focal point if it's a concave mirror, converging mirror. And if it is a convex mirror, diverging mirror, then it will go directly away from the focal point. So you can see that dotted line is going away from the focal point. Now, the dotted line here is a fake line. It doesn't actually exist, but it helps us when we're making the virtual images. And we'll see that below in a moment. But I also want to point out something compared to lenses. Concave mirrors are converging. So that's opposite of what a lens is. On a lens, it's convex is converging. On a mirror, concave is converging. And convex is diverging on a mirror. And obviously, again, that's the opposite for a lens. It's concave is diverging on a lens. So here you go. Let's take a look at the formula. Mirrors use the same formula as lenses. So 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image, including for magnification. We've got this formula here. This is the same as with lenses as well. Magnification is what's the ratio between the height of the image versus the height of the object. And it turns out that it's the same as the ratio between the distance of the image and the object to the lens or mirror in this case. Okay, so here is a little description of how we should draw this. It's sometimes not easy to draw, and it's hard to do with a screen. It's easier to do with a sharp pencil and a straight edge, possibly a ruler, but any sort of straight edge works. So we're going to go ahead and start drawing this. What we're going to do first is to draw a straight line from the top of the arrow to the mirror. So this is my first step. Okay, that's not in the best spot. There you go. Straight from the tip of the arrow to the mirror, exactly. Then once you get to the mirror, you're going to go directly to the focal point. And the focal point is always halfway to the center of the curvature. So this right here is what I get as my first ray. That's step 1. Okay, next, I'm going to draw a ray straight from the top of the arrow through the center of curvature. And this may or may not be super easy to do. when it's convex, but again, that's still not perfect. Yeah, that's still not perfect. Let's actually continue this down. Okay. I think that this one's not going to be perfect. Okay, let's try the next one though, and hopefully we're going to see this one show up. Actually, I'm going to use green because my purple is not as sharp. Okay, and then for the third step, draw a ray directly from the top of the arrow towards the focal point and then straight off the plane of the system. So from the top of the arrow to the focal point. Okay, and then based off of the plane of the system, i.e. like kind of horizontally. So we're going to try to draw that right now. Right there. Okay, and you can see here that it's not a very perfect diagram here, but hopefully you can tell that it's somewhere around here that we're going to have the image show up. Again, my blue line is certainly not perfect, but I'll try to just continue that down a little bit, and then hopefully you can see they kind of match. It's not perfect, but you can see they kind of match. So we're going to go with the red and the green. I think those are kind of a little bit nicer in terms of how well they matched up. And we're going to try to write down the characteristics of the result here. So the image is real. It's upside down, or better yet, inverted. Okay, and it's larger than the original. Okay, so if we take a look at the DI, we can count. We know each one of these squares here. It doesn't actually say, but we're going to pretend each square is 1 centimeter by 1 centimeter. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12.3 centimeters is my my estimate here. And the height is about almost 4, so maybe 3.9 centimeters, just slightly less. What we will say is actually we'll make that a negative because it is flipped. Alright, so that's what we have, but now we're going to try to solve it algebraically, and given the fact that we have we're going to pretend like the blue numbers are very exact. So DO is going to be 1, 2, 3, 4, 5, 6 centimeters away from the mirror, and HO is going to be 2 centimeters tall. Okay, so now what we're going to do is use the and we know the F. The distance to the focal point is 1, 2, 3, 4. So now we can use the formula from above. 1 over F equals 1 over DO plus 1 over DI. And we can rearrange this and solve for DI. So first of all, we're going to get 1 over DI equals 1 over DO 1 over F minus 1 over DO. Then we're going to basically flip everything. So it's 1 over DI. And when I say flip everything, I mean take 1 over everything. which will result in this weird formula. We're going to go ahead excuse me, and plug this in. So 1 over, and then do another fraction, 1 over f, which is 4, minus 1 over dO, which is 6. And so we get a result of di equaling 12 centimeters. Okay, so my result is not perfect. It should have been a little bit back, but that's okay. Not too bad. And then let's look at the HI. We're going to try to calculate HI. So this is using the ratio of the two. So HI over HO equals DI over DO. And so what we're going to do here is just find the ratio of the two to find our HI. So HI equals, and technically there's a negative if you really want to deal with the negative. So DI times HO over DO. All right, so now we can plug that all into our calculator as well. So we're going to go like this, negative DI, which is 12, times by HO, which is 2, over DO, which is 6, and we get negative 4 as our result. So again, it's negative 4 centimeters. This is very close to, but not perfectly, what we got with the graphical method. Okay, so now we're going to try this again with example 2. I'm going to just zoom out so you can see the steps. I recommend that you actually try this out yourself. You can always take a snip of this and then draw on it yourself, like print it out and draw on it, or you can screenshot and draw on it with your phone, or just overlay a piece of paper onto your screen, turn up the brightness, and then draw on the piece of paper. All of those ways just to get some rough idea of how to draw one of these ray diagrams. Okay, please try this out. Pause the video now, try it out, and press play after. Okay, so we're going to do this together now. Again, following the same steps as before. So we're going to, first of all, zoom in a little bit. First of all, we're going to do step 1, which is to do a straight line from the tip of the arrow to the mirror, which looks like this. Oh, that's not perfect, but it's the right idea. Okay, it hits the mirror there, and when it hits the mirror, it uses the focal point in order to draw the rest of the arrow. So this will hit the focal point. Again, it's not perfect, but neither will yours be perfect, so that's okay. Okay, again, not perfect, but we're going to continue the arrow off this way. So we know that the ray will leave the tip of the arrow going straight towards the mirror, but once it hits the mirror, it bounces off at an angle based off of the focal point. Now, we're going to do the next one, which is going to be based off the center of curvature. Now, the center of curvature is interesting because when you hit on a, especially on a convex situation, when you actually hit the mirror, let's just make sure that it's going to work on this side. Yeah, when you actually hit the mirror, it starts by going towards the mirror, and it actually will bounce straight back the other way. But if you continue the lines in towards, it would move this way. So already we think we know where it is. Keep in mind that first it starts towards, but then after it will bounce backwards, the same direction it came. Okay, now let's try the last one, which is to draw an arrow straight to your focal point. And it won't bounce straight back the way it came. it'll bounce straight back. So actually this one, yeah, no, this one doesn't work. So actually, sorry, we don't need that green one. We don't need that green one at all. That green one will not show up on a convex mirror. We can see that just these two will actually get us our result. So not super perfect, but you can see the idea. So now what we're going to do is we're going to draw the arrow showing up right about there. And because it is using these dotted lines, that means it's a virtual image. Okay, this is a virtual image. So we're going to write that down. We're assuming the same 1 by 1 square is 1 centimeter. So this is going to be a virtual image. This is right side up. So up, right. And this is smaller. Okay, and we can figure out the dimensions. So it is 1, 2, 3 centimeters distant from the mirror, and the height is 2 centimeters. Okay, that's kind of what it looks like here to me with my eyes. So again, is it perfect? Probably not, but hopefully this kind of works. Okay, so this is what we have here, and the one thing is that you do have to say is that the DI is technically negative here if you're using the negative in the magnification formula, or if you're talking about the fact that it's a virtual image, you're always going to have this negative focal length, right? As we talked about previously. So up here, it says that convex mirrors or any diverging mirrors or lenses always have a smaller, upright, and virtual image with a negative focal length. That's always the case for a diverging mirror or lens. So that's what we're seeing here. And because that has a negative focal length, we must have a negative DI to account for that. So another way to think about it is the distance to the mirror from the object is always going to be positive, but if you look at the distance from the image, if it's on the other side of the mirror, it will flip and become negative. That's one way to look at it. So with all that said, we're going to go ahead and try to do this with algebra now. So first of all, 1 over f equals 1 over dO plus 1 over di. We're going to solve for our di exactly the same way as last time, but I'm going to just do it a little faster. So 1 over f minus 1 over dO. It's the same steps as last time, and so now we can go ahead and try this in our calculator. So 1 at the top, 1 over the focal length, which is hard to see, but I think it's going from there. So 1, 2, 3, 4, 5. Whoops. 5, and then minus 1 over dO, which is the distance to the object, which is 1, 2, 3, 4, 5, 6, 7. It almost looks like it might be more at the beginning there a little bit, but we're gonna just leave it with that, and we're gonna calculate it. So we get 35 divided by 2, which is 17.5. Hold on. Oh, I made a classic mistake. the focal length is negative. And the, yeah. So 35 divided by 12. There you go. That'll probably get a better answer. And it is a negative result. So negative 2.9. There you go. Negative 2.92. Given we're talking about sig digs here, and I'm counting it pretty roughly, I'm going to be happy with negative 2.9 as our distance to the image. Okay, now we're going to go ahead and try to solve for our HI. Again, the exact same rearranging as before. So we would have started with HI over HO equals negative DI over DO. So if we rearrange that, we're going to have HO times negative DI over DO, which will give us negative DI, which we already know is a negative, so double negative, so 2.9 times HO, which is the height of the object, which is 1, 2, 3, 4, over the height of the distance to the object, which we said previously was 7. And so we get a result of 1.657. We're going to say 1.7. And again, this is not exactly the same as what we have here. In fact, it's a little bit worse, but maybe that's because our drawing is not perfect. Again, on a piece of paper, this should be a little more precise. But it's not too bad either. It gives us an idea of where it should land. Okay, so hopefully both of those ray diagrams helped you better understand that a little bit, and the algebra beside. But now let's go ahead and take a look at one more example. An object is placed between the focal length and a concave mirror. Will the result be a real or a virtual image, larger or smaller than the original? So this is kind of a little bit of a push ahead to just answer without a drawing. I recommend you pause the video now, try it yourself, and then go ahead and answer. Alright, so let's take a look at this example now. We're going to use our formula to try to solve this. The formula starts off looking like this, and what we're looking for is the result, the image, right? So we're going to solve for our DI just the same as we did in all the previous questions. I'm just doing it a little faster. So we have that, and now we can just make up some numbers. We know that the object is placed between the focal length and the mirror. So basically the distance to the object is actually less than the focal length. So 1 over f, the focal length, I'm just going to make something up, but let's say 10 centimeters, minus the distance to the object, and again, I'm just making something up, but let's say 6 centimeters. So if we solve this, it'll be 1 over, that's actually not going to be a nice, easy number, is it? Let's go ahead and plug this in our calculator. Okay, so we get negative 15. So this means our distance to the object, assuming we just made some of these numbers up, right? The distance to the object is negative 15 centimeters, which means it's past the mirror. The focal point is inside the mirror because it's a concave. If you were to draw this, it'd be concave, it'd be an arrow there, focal point here, right? Something like that, right? Now, that means that our image is showing up back here because it's negative. Now, this is a weird spot for it to be on a concave mirror. But the point is that you could have a virtual image and it is past this is past the focal point, which means that the virtual image is going to be larger than the original. So it's going to be larger, it's going to be virtual, okay, than the original. And in fact, I believe it should be upright as well. We can now go ahead and solve that. It wasn't asked in the question, but we can solve for that for sure if we plug it in to this formula. So now we can go ahead and solve for the HI. Okay, and again we can plug this into our calculator. Negative DI was 15, but it's a double negative because it's negative times a negative 15 times the HO, and again we can put in whatever number we want. So since I made it 6 centimeters away, I'm going to make it also 6 centimeters tall, and then over DO, which is the distance to the object, which I said was 6 as well, which means that it's going to be 15 centimeters tall. So again, I made the object 6 centimeters tall going to 15. That's why it's larger. That's kind of a proof. And it also shows that it's upright, but yet virtual because it's on the negative side. Alright, I hope this video helped you better understand mirrors. I hope it was helpful, especially with these ray diagrams and these calculations. Hope the video helped, and good luck.